it all day. Everyone, welcome to another installation of Zach's podcast, or whatever. Is it a podcast? It's live development. So let me write the description for today's stream and then we can go on. Let's attempt to use CMSIS for MFCC feature extraction from some audio samples. Let's attempt that straight. I kind of need to preface this a little bit because it's not as straightforward as it seems to do this. Well, it really is straightforward to do it. It's just not when you're working on something, isn't as straightforward as just getting the features and then you kind of won. Getting the features is kind of the first step to it of the first step of the whole project. Well, it's not even the first step, it's like somewhere in the middle, but this is all stuff that will come to light. What I do want to sort of highlight is what we sort of want to end up doing and how we end up getting there. So, first of all, what is MFCC? MFCC. So MFCC, the best way I can explain them is like features in audio. It appears to be these features in audio that are almost like linearly kind of spaced, which is a lot to say in like the first minute of this thing. But it's just elements of signals that appear in audio that you can use to identify where the audio came from. That's basically what MFCC is. If you go into it, you can use it from that rather than that, but like assume it's like signatures in audio that can tell you the person who's speaking, that can tell you which microphone they used to record, that can tell you the sort of like algorithms that the microphone was using. Let's actually read this out and then we'll go towards the code. In sound processing, mouth frequency spectrum, MFC, is a representation of the total power spectrum of a sound. So power spectrum, that's sort of like a little, it's like looking at the wave of something. Yeah, exactly. So you get this little blips. You see, you get this little blips, and then depending on how big these blips are and how far they are from each other, you can kind of identify. It's like a little signature in the sound about what made this sound and all those things. And they appear a lot in speech. So they're not just exactly just sound. It's just like in audio. They're also like they appear to be just in speech actually. Just let me see. Let me go fix this. It appears my audio is not working. Okay, so something about my audio is broken. Let me fix it. Let me see. This is not cool. Properties built-in unload. Yes, yeah. I actually think it's a bit too high. Maybe. Okay, cool. Just ask them if it's okay. Yeah. So let me know if my audio actually breaks up again, but it shouldn't. Hopefully it doesn't. Hopefully it doesn't. Hopefully it doesn't. So it shouldn't though. Something's cutting off. If anyone's online, please let me know if this is better audio so I can go on rather than making a whole video with broken audio. Is this better? But Kara and Bartholomew. So it's broken still. The PS is still broken. It's like, how is it breaking? Okay, so let's try and fix this. That's bad. That's bad if you can't understand what I'm saying. Let's see. Okay, let's try now. Testing 1 2, testing 1 2. Is it working? Is it working? I mean, it's actually, I can't actually talk. Okay, that's that. Plug that in. That's a lot of activity actually. Filters. Something about OBS is like I either messed it up or somehow can we okay, just a moment now. Check now. Testing 1 2, testing 1 2, audio check 1 2, testing 1 2. Doesn't work. Does it work? Is the audio working? Is the audio better? It's completely broken. I wonder if it's my internet. Oh, yeah. Thank you, Bartholomew. Thank you, Bartholomew. My phone was right next to my computer. Maybe that fixed it actually. And then also there is a Bluetooth device here, but that shouldn't actually fix. That shouldn't be. Let's see now. Testing 1 2, testing 1 2. Testing 1 2, testing 1 2. Checking. Does this work? Does this work? Does the audio work? Can everyone hear me clearly? It's still broken. Where's the source of this interference? Let's take this out as well. Okay. Just take this as well. Testing 1 2. Huh? Okay, let me restart the stream again and see what happens. Yeah. Okay.
10 seconds behind.
Okay, let's see. No, it started again now. Okay, good, excellent. No, Bartholomew, I'm back. I had to like kill the stream so I could come back. It's okay now, he says. Okay, thank you, Bartholomew. It's okay now. Thank you. Where were we? MFCs. So basically what you have on screen is the where is it? Is this nonlinear mel scale? This but this little image on screen shows us what the spectrum, the log power spectrum is. So we have this little blips. See, we have this little blips on the audio, and those little blips can help us identify what sort of made the audio. Okay, so that's kind of what we are going to be doing, I think. Yeah, it works. Cool. I'm just worried about all my audio and everything. So that's kind of what we're going to be doing today. We want to kind of build through and see if we can identify whether this thing works or not. Okay. Just one moment. Okay, cool. So let's actually walk through this thing and see if we can fix it. The first attempt we did last week is the last time we... Cool, thank you. It doesn't really matter. It's very difficult to find the information about that. That's just my notes. So last week we... yeah. Applications. Zephyr custom. Yeah. And then I think here, yeah, that's just BC. That's just a calculator. So you don't need that right now. Yes. Yes. Yeah. And then we can do Control Shift T, and then in here we can do source, go home, go into the Zephyr project, and then .vn, then bin, then activate. Cool. So we have a Zephyr environment there. So the other thing we can do here is actually just add a logger of this thing and see. Control R screen. I think this is supposed to be SCM0. The device here is SCM0, and I think I'm gonna just plug this guy in and yeah. Pause. I need to get my phone because I can't activate the button without my phone. Okay, cool. And I'll make sure to keep my phone far away from my laptop so that if I have any signal interference, we can work. Okay, cool. And let me know if signal interference comes in through now, please. So I'm gonna connect this and we can see what's happening, and then we'll start fixing from there. Bluetooth. It's a Bluetooth device. There you go. So let's connect it. Yeah, that's our big problem. I'm only getting zeros right now, and I think let's start fixing it from there. So let's see if we can fix it from there. You shouldn't, yeah. You shouldn't keep going. Or is the logs catching up? Why are you running inference? Why are you going into mic capture and we're not connected? That's a problem. This is a problem somehow. We shouldn't be seeing this. So it appears we never actually take that semaphore back. There's a problem. Let's actually go fix this now. There's a problem. In disconnected, we are still, there's a semaphore somewhere that we're not applying. Yeah, I can see there for same service. So let's actually see connected. Where are you? Yeah. In idle you got connected. Yeah, cool. Yeah. In connected entry we allow the thing, yes, but yeah, let's see disconnected. Disconnected. There's no disconnected state. Okay, let's go see. There's no disconnected state. There's an idle state. Okay, so let's see disconnected. So if you're in connected, you go to idle. Okay, so if we're in idle, yeah, create idle entry, idle run, idle exit. That's fine. Idle entry, idle entry. Yeah. Here. reset makes sense. Yeah, this is fine. This stops it, which is quite odd. Why is that? Entered idle. Oh, I think I know the problem is let's go and look at mic capture entry. Audio sense end goes to inferring, and then let's go to the inferring entry. Kim give. I don't know that we want to give this semaphore here. But it also doesn't matter because do we need to handle being disconnected here? Because if we are disconnected, if we're in disconnected and we're in the inference state, then we should actually stop it. I'd like to handle the disconnection there because that means yeah, I'd like to do that. Yeah, let's go into idle. If we do disconnect, let's go into idle. Yeah. Let's go into not my capture entry, infer entry. Yeah. And then I'm gonna do an else and then a P. And then this should actually fix something. Let's start by building this. Just so what I want to do is, if I disconnect while I'm in inference, then I would like to respond to that. But even then, no. Anyways. Okay. Let's actually just file a bug. Let's file a bug, no? Let's file a bug and we'll come back to this later. Otherwise, we're gonna just lose the whole thing. Let's file a bug and we'll come back to this later. Issues, let's file a bug. Handle states handle disconnection event from all states. So when the central device disconnects, we need to handle this event across all the application states. Okay, that's fine. We can leave it at that. And then we can always detail this when we start coming to work on it. Let's file it. Okay, in the first thing. So the first thing we noticed is that sorry about that. I just do want to do git status so that we don't have any git diff. Okay, git checkout. Let's do that. No. Git checkout. Git status. Cool. We are back on where we want to be. So the first thing I want to do is I want to go to the. Do I have stuff here? I want to go to the audio. No, the inference service here. And before we even get to the filtering and everything, here I would like to log. Yeah, it's fine. Log error so we can see it. Sample D is F, isn't it? Yeah. So here I want to do F, and then I want to go like F, and then I want to do double sum. Yeah, no, so sample. I don't want to compute this twice again, so let's go like yeah, float 32t f sample equals this whole thing here. It's okay, it's fine. Yeah, this, and then I can go here in sample f is equals to f sample. This is just a placeholder stuff because we need to I just want it like this now. Okay, cool. Sure. That's why I made that. So I said I want to do F sample. Okay, so let's build this, and then we can do some questions, and then we can come back to this. Welcome. As always, let's fix some stuff here. OS build -b nrf 52840 dongle, and then nrf 52840 yeah, that's pristine. Okay, we can do questions now. While I'm building this. So I'm building this so that we can observe the samples before we do anything to them. I'd like to see if actually we are getting the samples as we need them from the microphone, and then we can move on to doing some MFCC from them. I do have a few ideas of how we're going to be able to debug this. First of all, we need to check whether the instance is coming up right, and then beyond that we need to probably, yeah, it's fine. We are not using the FIR state right now. I just want to see that we're getting the whole thing in before we do anything to it. In any case, it appears we actually do have to make FFT samples. We have to transform our samples from normalized stuff to FFT. We have to do a Fourier transform on them so that we can actually hand the Fourier transformed information into the MFCC extraction thing, and then we can actually extract. Yeah, but let's see. Any questions so far? Any questions so far? Please do leave them in the comments. Remember, in the description there's a link to our Discord community. You can join us and we can talk about stuff, and you can always ask more questions there and stuff. Let me check. Cool. start building, and then we can start deploying and seeing what happens there. What happens there? It is said that when you learn, you want to learn more. And I'm very stuck in that place right now because I'm learning and then I want to learn so much more. Cool. So it's there, and then I presume I can do a Control R and find a dash. Oh, Control. Oh, okay. It's wrong. Control R here, and then I can find. What I want to find is dash HW. Yeah, cool. So this is just a packaging command. What it does is makes a zip file, and then we can use the zip file on our device. Yeah, and then I need to put this thing on bootloader mode. Bootloader mode. Okay. Today is a really odd day. That's very odd. That's very odd. Did I fry my thing? Is my board broken? Okay, cool. It's blinking, which is not a good thing. DFU. Let's try and package in something. Let's see what happens. Okay, kind of works. Yeah, it's flashing. Cool. It's flashing, and it's flashed. Okay, let's now actually pull up some logs from this thing. Cool, it's on. It's fine. Okay, let's see. What we're aiming to see is some sort of data, any sort of data. If we can get actual fractions, actual floating point data on the screen, then we're good. We can move on to the next thing. Okay, cool. I'm gonna connect now. That's not good. This is absolutely not good. Bartholomew, is this what is breaking for you? Yeah, this is actually not good. This is not good because, yeah. Why are you going on? Why are you not stopping? There's in some weird way we changed something somewhere. Okay, cool. So let's look at this samples samples. Something here is wrong. Something here is very wrong. Let's fix this. Something here is quite wrong. I see an issue. I'm doing two sorts of FFT sample, yeah. Okay, cool. So that's fine for now. I should not do this. Let's remove all of that. Okay, cool. Let's actually remove that, and then let's see what happens. Let's rebuild it. Any questions so far? Any questions on this? I have a feeling we broke something in here. I'll show you where. Let's go here while that's building. Let's go here and then let's go into our here. Let's go to pull requests. There's some code we must have changed here that broke everything, and that's fine. Now built this thing from scratch, so we can fix it. I sort of wanted to highlight some stuff, but let's see while this is building. It's going to take a while. I think it's going to be here. This was all added. This is a new file. Okay, cool. I might have to go commit by commit because at some commit this was working. Samples that I want to see here without all of this first, and then we'll decide. Yeah. So while that is building, let me go and see if I can describe some stuff for you. So the thing about MFCCs is we're going to use them sort of like this. I need to find that there's a really nice description here. Yeah, actually here. Box. I should put this in the link then. So this is a tool that I've used before, and that actually describes the whole process really nice. Let me add to the link file, to the description video so that you can get it. Links. Okay, cool. Yeah, this link is in the description of the video. So I want to go to docs, and in docs I want to go to the use cases, and in the use cases I want to go to something called keyword spotting, so that we can look at it actually. And this is, if you come and read this is just basically how you do keyword spotting end to end, and this is Alif make a kit that comes with some code that is on it that you can use. They use an NPU which is for different state. Maybe at some point I'll do this on the stream and then we'll look at it. But what I want to show you is that how MFCCs are used. So what you do is you maintain like a streaming MFCC inference. You hold a number of windows, preferably the number of windows that's going to allow you to do the MFCC feature that you want to find. Once you hold that number of windows in samples, okay, you hold a number of samples. So say something like 16,000 samples. That's what you're going to use. For us, it's something like 4096 times 3. I don't know how many samples that is. But you hold them, and then what you do is instead, this is something that broke, that didn't work for us before. Instead of trying to compute the MFCC all at once for the whole thing, what you want to do is you want to compute some sort of like running MFCC feature set. And then in this, as you're computing this running MFCC inference, whenever some running value is equal to the one that you're looking for, then you start doing actions that are demanded by your inference. But the more implemented, the more our implementation will start looking like this. But so for now, let's make sure that the data is coming out of the raw data first. Okay, cool. So after this, I need to pack it. Let's pack it into an fft.zip. That's cool. And then I'll put this thing in bootloader mode. It should go. It did go once. And then I'll go here and I'll do DFU and up into it. That's the first thing. Cool. Cool. I really need to find out where that bug is that just lets the thing run after disconnect. So let's connect here. It should be good. It should be actually connected. I bet you it's connected. I don't know. Is that a reset button? No, that's not a reset button. But let's see. If I connect, we should get some logs. Yeah, this is not good. Yeah, okay, so this is better. I'll do that, and then I'll do that, and then I'll do this, and I'll do this. Okay, cool. So this is going to be much better. Okay, so let's connect. Perfect. This is good. So what we can see here is that our actual samples are getting to the device. So it's not that our samples are not getting to the device. They are getting to the device. We do know one thing. Disconnect does not work. It should stop now. It should not go on. We should not see some red logs again. But we do see red logs. It should never get to there. It should never run audio, which should never run inference. So there's some signal, there's something. Disconnect does not disable what it's supposed to disable, but we'll fix that later. For now, we have the data, so I think let's start actually working towards getting MFCC coefficients from it, and then we'll go from there. We do have the data, so this part actually works. This part actually works. This part actually works. This part actually works. I don't know if you guys saw that, but my kitten was trying to open the door. Yeah, so we can get all of this, and we're getting samples, and the samples are exactly what we expect. The first thing I want to do is let's actually now go back to this function, RFFT from CMSIS. So let's go back to RFFT, and you can see what where I'm going with this. The first thing we want to do is, before we get here, we want to get to the transform functions. Cool. And then we want to go to the real function, real fast Fourier transforms. Fari. I don't know if you say Fari or Fourier. I think it's an F32. And then the first thing I want to do is we want to use this guy. Look, there's a function we call here. ARM RFFT fast init this. Okay, this actually returns fast init 4096 F32. So cool. This 4096 F32. This. Why is there a generic one? And then let's actually find out. This might be why we're broken. So there's this generic one. Yeah, but I don't need to do this because it's one of those. So yeah, that's cool. That's fine. So this is the same thing. So we're going to use this 4096 one. Let's see what it does. So it either returns one of these, and I think the thing we want to do right now is to check one of these returns. We need to check it so that we know why we're getting zeros, really. I want to know if it's successful so that we can use it later. This is basically now debugging it. Okay, cool. So this actually returns something. This returns some sort of... what is this? What are you? What are you? It's an enum. I guess I can get ARM status somehow. Okay. So let's actually just go here and say something like ARM status S FFTS is equals to that. Is that okay? Yeah, that's fine. That's okay. And then we want to do something like I want to do log error so that we see it. FFT init status. If I print it in a D, will I still get it? ARM status. Unexpected thing, FFTS. Okay. Will I still get it? It seems like I will get it, but let's see. Let's now actually build this and see, so that we know whether that thing is actually getting instantiated the way we want. I have a feeling it's successful, and this is just like yeah, let's build it. Any questions so far? While that's building, that takes a while to build. While that's building, let's come and look at this. Let's come and look at this. Perhaps in here we can find out what happens. Yeah, let's look at this. So in this, what do? We add an inference gate, and we do that. Audio sense started, audio sense ended, inference started, inference end. That's fine, that's okay. And then in here, what do? We define a 0 inference get 0 1, that's okay. And then we define an inference state. And then we say, if this is where is this? This is in, where's this? So no, this is not the one we want to look at. Look at the disconnected one. Sorry. I would like to look at this while it's building. I'd like to look at it. So if event audio sense started, so this doesn't make sense. Yeah. If you get a disconnected event, go to idle, that's fine. But yeah, if audio sense started, go to my capture, that's fine, that's okay. But then there's this other place. So, audio sense end in firing, cool. In firing entry, that's okay, this is okay. Once we're done with audio sense, we go to inference, that's fine. And then once we're going into inferring entry, it's here, we go there, and then we go here. I think we need a child state. Or a, so once we've finished, this is a problem. Once we've finished inference, we go to connected, which is fine because we should. I don't think we should give this semaphore. Yeah. Do we actually take it? Yeah, cool. Should we give it or reset it? I think we should maybe reset it. KSEM reset. And it's KSEM reset. I only have 15 minutes, I'm sorry guys. So busy these days. KSEM reset. We should receive a disconnected event. We do receive a disconnected event. But that disconnected event does not seem to take away the power from the mic. Do we want to do this here? I'm wondering if we really do want to do this. I'll try and remove it in the next iteration so that we see. Okay, let's flash this. First of all, we need to pack it. I forget, what did we change now? What did we change now? We're looking at the status. So cool. So this is actually this one's actually quite easy. We've done that. We've packed it. Let's load it up. And as soon as we load it up, we should be able to just kind of get into it and scroll. Yeah. FFT needs set status 0. So the other thing we now need to go and find out is I need to find out where that's a problem. Where's KMSIS DSP? This error math access. Because that's what it gives us. That's what we get, no? That is what we get. Math success, this one, or argument error 0. So what we need to find out is this a 0 or is this a 0? So we need to go into probably KMSIS DSP GitHub. It's fine. Yeah, maybe. Yeah, maybe. And then we need to find out, what do we need to find out? We need to find this one. This is some enum. This is in an enum. And this enum is ARM status. So ARM status. ARM status. Where are you? How do you define? Yeah. It feels like this is the one. ARM status. Please go away. Oh, come on. Where are you? Okay, math success 0. So we've confirmed. Our initialization of the FFT init is working. Cool. We've confirmed that that's working. So FFT is being initialized properly. So this works. We can actually remove this because we know now. Well, we can always just log one. So we don't have to actually just we can actually go, while one. Yeah, okay, cool. It's fine. This is okay. It's fine. Initialize status, that's cool. So okay, so now actually let's actually go to the next part. This doesn't return anything, so we're kind of in a bit of a problem there, because this doesn't return anything. This is a void. What it does is fills this FFT samples. GD. It is samples per block. We do so. Yeah, it just fills that thing. Yeah, cool. So it just fills it. Control row. So let's look at this. ARM, RFFT, real fast Fourier transform, and then let's go actually look at what it does. Sorry, today is just a debugging session, it seems like. This is an initializer, but what we need here is ARM RFFT fast F32. Okay, there's no init, just a fast F32. So what does this do? Processing function for the floating point real FFT points to input buffer. So S parameters, S points to instance. Okay, cool. So this is the instance. Cool. and then points to input buffer. Cool. So that points to that input buffer. That's okay. That defines an array, so that's fine. That is the samples, which is samples F. Do you see what I'm seeing? Do you see what I'm seeing? Samples F. F sample. Samples F. Samples F. Do you see what I'm saying? So this is not a samples F. But then there's a samples. There's a samples here. You see these samples here? Okay, let's just migrate to that and see if that actually changes anything. We'll get to this. What is this? Incompatible int32. Cool. Okay, so let's fill the right one here. So this is samples F. Let's fill the right person here. Okay. So that's okay. So let's say samples F equals to that. Cool. And then if we do that, it will be cool. That will be okay. And we'll get what we need. So I'd like to remove this. And I would like to not use yeah. And then let's do this. Samples F. Here, let's actually do that, and then I'd like to what I want to see here is this. So I just want to see them so we know it was computed, and then next time we can work on the synchronization error. And you see this is filtered samples as well, so we were quite wrong. We were quite wrong in the other things. So samples F. So our code before was quite wrong. So this fills samples F. This uses the source array and fills FFT samples. Aha. Cool. Bear with me here. I'm sort of working from memory, and I'm working with very little context. I keep forgetting what I'm doing, and then I have to go fix a lot of stuff at work, and then I come back and I don't know what I'm doing. But this is normal. This is how I work. I think that's development for everyone. I don't have that much time, but let's do it. So RFFT fast F32 takes an instance of a FF2 Fourier transformer, and then it points to the input buffer, which is samples F, which is the one we're filling up here, samples F for sure, and then it points to the output buffer. There you go, FFT samples, and then it points to an FFT flag, and the FFT flag is 0 or 1. If it's 0, you're getting the real fast Fourier transform. If it's 1, you're getting the real inverse one. So let's actually just GD, what are you? You're a 0. Control 0, Control O. Let's go back to where we were. Okay, cool. So this feels like it should work now. And this gives us FFT samples, and then here we log out FFT samples. So let's see. This might actually be the thing that works for us. And then if it works for now, we can stop, and then we can do a part 2. Well, we have to stop anyways, but we can do a part 2 in a couple of days, or tomorrow even, where we actually go and start extracting this MFCCs. It really is quite simple, because once we have the FFT samples, we can just pass them straight into the, let's actually just look at it here, F32. So you will notice here that, so we're going to use this one, 4096 again. It'll take we'll have to make some filters, we'll have to make some discrete cosine stuff, and discrete cosine coefficients, and filter positions, and length, and all of these things. This is all stuff we're going to choose based on based on something like this. This is what is going to inform us. So we're going to say something like, how big is the window, how big is the window, how big is the frame. It's explained somewhere here. That's easy. Yeah, so this whole thing, first the audio data is now normalized. We're doing that. Next, a window of 640 audio samples is taken from the start of the audio clip. Then from this 640 samples, we calculate 10 MFCC features, and then we're gonna build up to something like this, which actually changes quite a bit, because we have to now, because we want it running. It's for another stream, but because we want it running, we're not going to be able to do the whole window at once. We're going to do, and because we want it fast, we want to be able to infer really quickly. So we want to, what you actually want to do is to maintain a running MFCC feature set or something of the sort. But for now, let's actually build this. I think so. What I wanted to demonstrate here by coming here is that we need to pass in into this. We give it we give it an FFT. How do I see this? We give it an FFT sample set. So we have to do FFT in order to get to this. Anyways. Okay, cool. Let's build this. Any questions so far? Any questions so far? While this is building. This is gonna be the last build of the video, and then I have to run because I have a meeting usually. I have a meeting at work on Mondays at this time, so that's why the Monday stream is at 3 p.m. and not at 4 p.m. Any questions? Any questions? Bartholomew, maybe if you try the fixes that I've applied just now, maybe if you try those fixes, it would actually give you output on your end. Because we were getting zeros, so it could be that I was pointing it at the wrong place. I'm sorry about that. Almost done. Takes a bit. While this is running, let's actually go back to the thing that we were looking at. So let's read this, and by the time we're done reading it, it should be done. So, introduction. This document describes the process of setting up and running the ARM Ethos U NPU keyword spotting sample. So this sample that we are reading right now, it runs on an NPU, but that's not a different thing. It's just a coprocessor that is. When you hear AI accelerator, this is kind of the thing. So it's either like, yeah, whatever. So this document, pre-processing feature. The micronet keyword spotting model that is used for code samples expects audio to be pre-processed in a specific way before performing an inference. Okay. Therefore, this section aims to provide the overview of the feature extraction process used. First, the data is normalized -1 to 1, so that's from that range. Note, Mel frequency septal coefficients are a common feature that is extracted from audio data and can be used as an input for machine learning tasks such as keyword spotting and speech recognition. For implementation details, you can look at this. You can look at this kind of file. It's in there somewhere. Next, a window of 640 audio samples is taken from the start of the audio clip. So this assumes that you're running, you have all your audio, you have your whole sample at once, and then you want to like infer on it immediately. From this 640 samples, we calculate 10 MFCC features. The whole window is shifted to the right by 320, so there's some sort of overlap. Remember, they're doing 640, 640, 640, but they're only shifting to the right 320. So if they're shifting to the right, on my screen it might look different, but if they're shifting to the right 320, that means they're still holding some of the 320 that they just calculated for. So they have this overlapping feature basically that's going on, and that overlapping feature is the thing called windowing. We should have covered it a few weeks ago in some sort of DSP thing that I did. Okay, so the whole window is shifted to the right by 320 audio samples, and 10 new MFCC features are calculated. This process of shifting and calculating is repeated until we reach the end of 16,000 audio samples required to perform an inference. And then once that is done, it's good. So what happens here is actually what you want to do on your own devices. You want to if you want to do inference really quickly, you don't want to do 16,000, then you do inference, then you do 16,000, then you do inference. That is sort of why we had to build a different thread in our application, because if you do that, then it takes so long to inference that you're going to mess with the recording stuff and you're going to miss stuff. So what you actually want to do is you want to record, say, 640 samples, and then do inference on that, hold that, and then do another 640, and then 640 and 640, and then you keep going. It's 49 times basically. You keep going, and then for each one of them you compute 10 MFCC features, and this is now like some sort of running window, sliding window, if you could call it sliding window. And this is shown actually in our in this one really well. So you get 640, 640, 640, but instead of this 640, you're not just doing 640 and moving to the next one. You're doing 640 and then you're moving to half, and then you're doing the, so the half is usually half of this current set and half of the next current set. So you have this sort of sliding function. And what you want to do is you want to, ideally you want to accumulate the first 49, and then from there on you drop the oldest one and you just accumulate 1, 1, 1, 1. So every time you drop one, you add one, you drop one, you add one, you drop one, you add one. And what this does is it gives you a buffering system where you are calculating inference for just the last window. And that becomes fast because it's really quick to calculate inference for 640 samples rather than for 4096 samples. So if you do that and you build up and you build up and you build up like that, you basically end up holding this sort of memory, and you go like, in the last 49 has it happened? No. In the last 49 has it happened? No. And every time you ask, you're adding one, removing one, adding one, removing one, adding one, removing one, and you're maintaining this sort of running window or sliding window of inference frames. Anyways, that's good. So that's built. Let's actually pack it into F50. I would be overjoyed, ecstatic if we get F50. That would be kind of like a big win for me right now. And then let's actually push it onto the device. That should go. And hopefully this actually does give us F50 samples, and that would be a good capstone for this stream right now. So let's see, should get some output hopefully. Yeah, cool. So let's actually now connect this. Let's see. So I'm going to connect. Bartholomew, we have code on the screen and it actually does inference. Where's Bartholomew? There you go. So cool. So number one, we've gotten the F50 of our signal. So the next time in part 2 of MFCC feature extraction, now we can actually use this F50 and go and extract features from there. Let's write a comment and we can finish today's stream on a high. That's really cool. That's really cool. Get status. Hopefully just one file change. Get diff. That's all. Okay. Get commit -m inference. Check let's actually do a V so it's easier. Yeah, git add src git commit -v. Okay. Inference fixes. Check status of FFT instance of KMSIS FFT instance. Compute FFT of signal and hold it in the right buffer, and then we can do that, and then we can do a git push. That's it. Okay, anyways, thank you all so much for coming today. Here we go. There is a pull request to this. Let me pull it up. There's a pull request to this, and if we do a refresh, you shall see that our new code is going to be reflected. And yeah, so we actually got to a point where we can see the FFT of the signal, and I presume it's still running somewhere here. So we actually get FFT samples, which is amazing. So we're kind of half of the way there. And now we need to find out how to hand over these FFT samples into our MFC feature extraction, and then that will extract the feature for us. And then we'll have to pause this part of the project and go and look at like a machine learning model, and how to build up a machine learning model from this, and so that we can apply something and we can actually get Jarvis going on. We're building a Jarvis keyword detection. Cool. Thank you all so much for coming today. That's me. This is Zach. Welcome to Debugging with me, and I'll see you guys next time. Thank you so much. Cheers. That's been amazing. Bartholomew, I see you. We'll talk later. Amazing.